I want to talk about section 8.1 immediately after 1.1 because the techniques of solving problems in 8.1 are about the same as what we do in 1.1, and a lot of the story problems are the same. So 8.1 is about systems of equations, simultaneous systems of equations. That means, for instance, a pair of equations like this. Two equations with two unknowns x and y. What I'm looking for is a number x and a number y that makes both equations true at the same time. That's why it's called simultaneous. Like I can see in the first one that x equals 1, y equals 1 would satisfy the first equation. But x equals 1, y equals 1 won't satisfy the second. So I'm looking for the pair of x and y that goes together that satisfies both of them at the same time. Usually solve this by means of what's called substitution. Solve for either x or y in either equation that you like. I think I'm going to solve for x in this equation. Remember, solve for means get x by itself on one side of the equation. Not necessarily find the numerical value of x, but get x by itself. So to solve for x in this first equation, I would subtract 5y from both sides. So the left side will become x, and the right side will become 6 minus 5y. Now substitute that back into the second equation. And the second equation will become 2 times 6 minus 5y minus 9y equals negative 1. Now it's just one equation and one unknown, y. 12 minus 10y minus 9y is negative 1. So I collect up terms. Let's subtract 12 from both sides. So the left side is, the 12s are gone, negative 19y. And the right side is negative 13. So if I divide both sides by negative 19, I get that y is negative 13 over negative 19, or 13/19. Now that I've learned what y is, it's easy to find x because I've got this expression up here that allows me to just plug in any y value I like and learn what x is. So the corresponding value of x must be 6 minus 5 times 13/19. Remember, to multiply a fraction by a whole number is to multiply, like in this case 5, by 5 over 1. So the 5 just multiplies in the numerator. What's 5 times 13? 65? 65 over 19. To complete adding these guys, I think I need to write 16, or rather 6 as some fraction with a 19 in the denominator. I just squeeze it in here, multiply top and bottom by 19. What's 6 times 19? 6 times 20 is 120, so it must be 114. 114 over 19 minus 65 over 19. That must be 49. Yeah, 49 over 19. Beautiful. So the solution is, just to underscore this, the solution is x equals 49/19 and y equals 13/19. The solution is an x and a y value that together make both equations true. Well, that one had a lot of fractions in it. Generally, I try to make up story problems for my students that don't have maybe that much arithmetic. I don't think it's bad for you to, I think it's okay to expect you to do some arithmetic on an exam and in the homework. That might be a bit much. I'll have to think more carefully about the next problem. I think this one won't be so bad. So suppose the equations are x plus y equals 1 and 3x plus 3y equals 2. So it'd be easy to solve for x or y in the first equation. Well, let's solve for y. By subtracting x from both sides, y is 1 minus x. And now I'm going to plug that into here. And the second equation becomes 3x plus 3 times 1 minus x is 2. So that's 3x plus 3 minus 3x is 2. And look what happens. The 3x's cancel, and this says 3 equals 2. There aren't any x's that could cause 3 to equal 2. So this system has no solutions. I mean, there are x's and y's that could satisfy the first equation or the second, but not simultaneously. When I look back on it, I can see now why the system had no solutions. Look, the left side of the second equation is exactly 3 times the left side of the first equation. But the right side of the second equation is only 2 times the right side of the first equation. If x plus y equals 1, then 3x plus 3y would have to be 3. It couldn't equal 2. It's also possible for systems to have, let's see, in equation, in example 1, we saw a system had exactly one solution. This one had 0 solutions. It's possible for a system to have infinitely many solutions. I'll show you what one of those looks like. Here I kind of cooked it up so that we had infinitely many solutions. Notice the second equation is just 3 times the first equation. So let's go through the mechanics of solving it. If I went to solve for x in the first equation, I'd get x equals, I would have to add 2y to both sides. X is 2 plus 2y. And when I plug that in here, the second equation becomes 3 times 2 plus 2y minus 6y equals 6. And now I go about solving. 6 plus 6y minus 6y equals 6. Look, everybody cancels. 6 equals 6. That doesn't really tell me anything about y. That's because y can be any real number and satisfy this. Does that mean x and y can just be any old thing? No, x still has to be 2 plus 2y. So the solution is y can be any real number and x equals 2 plus 2y. And there's the solution to that system. If you think about it, there's infinitely many choices for y, and so there are corresponding choices for x for each one of those y's, but that's still infinitely many pairs of x and y that satisfy those two equations.